Hello, Internet. So, as I've been thinking about ways to add optimizations to my C compiler that fits in one JavaScript file, I came across this classic optimization that I don't know. Every time I see it, it still kind of blows my mind a little bit. So you have this simple loop, but you see that when you compile it with Clang, you get this. Like you don't have to be an expert in assembly to see that. Wait a second, there's no loop here. This is it. This friggin' loop compiles down to this, which is just like a number, right? It basically looks like Clang pre-calculated the number and then just shoved it in there as a return value. It's wild, right? And then so if you think like, okay, well, maybe it's just something to do with like constants, and then the compiler kind of knew what to do. You could substitute an argument here, right? Then what is Clang going to do after that? It actually still gets rid of the loop. Again, like there's no loop here. This is just a set of computation instructions, and essentially boils down to this formula down here, right? Which is like actually the formula for how to get add numbers up from 2 to whatever n minus 1 or whatever, right? But like how did Clang come up with that formula, right? Like why is this optimization here, right? Like this essentially what happened here was we went from here, this code, and then Clang looked at it and decided that nah, I'll just emit this instead, right? Like too much. Where did this optimization come from? Well, my first thought, right, was like, okay, the way it must have, like, my first thought on how they must have implemented this was, like, they must have looked for certain patterns in the compiler, maybe certain patterns like x plus equals some formula based on the iteration variable, and then, okay, well, like, you can happen to solve the formula, if you see this pattern and then convert it down to this. In spirit, in a way, it kind of is what happens, but in practice it isn't. Clang actually doesn't do it exactly this way, right? So, okay, like, my second thought was, okay, maybe it's loop unrolling, right? I know that compiler sometimes when it knows the loop is bounded, it'll create, like, it'll actually write it out to avoid doing branching and loops, and so it'll just compute everything unrolled. And when you see the formulas unrolled, maybe you could also imagine fathom a world where, like, okay, well, I know the initial values and I happen to see the formulas for how these values evolve, so you can keep track of it kind of like this here, right? It turns out this is also not what Clang does, because first of all, in the first case, when you're going all the way up to 1,000,000, unrolling a loop of 1,000,000 is a little bit crazy. It wouldn't do that. And secondly, in the second case, it's not. You also don't have a constant number. You actually don't know how many times you have to unroll. So this idea doesn't quite work. So basically, a lot of these compilers, when they do optimizations, they store the program in what's called single static assignment. Single as in once, static as in not changing, and assignment as in setting the value of a variable. So in the static single assignment, single static single assignment. In SSA, you're only ever allowed to store a value to a variable once. But then you might think, wait a second, like my program has mutations everywhere. Like I have value of x changing, I have value of I changing. What do? Well, every time you assign to it in SSA, you create a new variable. Essentially, you have, initially you have I equals 0, x equals 0, and then whenever you have a situation where the value could have come from two different places, you represent it with phi, and then you store the two things it could have been. So in this case, for example, the assignment in I++ here, I1, well, it could have come either from the value of I before starting the loop, or it could have come from the value of I after incrementing in the previous iteration of the loop, right? Same for x. X starts out as 0, and then x also gets updated later in the loop. So when you're assigning x1, you could either have gotten this value from x coming from outside of the loop, or you could have gotten x from the value x2, which is the value of x you got from incrementing, updating the value of x in the previous iteration of the loop. Right? It feels a little bit roundabout, but this is quite standard compiler fare, from what I understand. And once you store it in this format, it is a little bit easier to identify certain kind of patterns, like when you notice that a formula evolves as, like a variable is essentially evolves as a recurrence relation. When that is the case, there are some general formulas for calculating it, and then you can simplify to find that the formula becomes this. And when it's identifiable, the compiler will actually just substitute the value. You don't actually completely have to understand this to apply it. Essentially, the algorithm is something you can follow. I guess is the thing you could do. There's an algorithm for identifying the recurrence relations itself, the chain of recurrence relations. Like I is essentially a recurrence relation of I equals I plus 1, right? And then you have X, which is a recurrence relation that contains I. But even in those situations, we have some magical formulas. If you've essentially calculus, but for discrete numbers, that will give you this formula to figure out how to compute them in a closed form. Which I think is pretty magical. Like when you're doing programming, quite often you're like, do you really need math in programming? Well, turns out like math really does help sometimes. One of those rare cases you actually see some math while you're doing programming. Like the loop itself is not something you see all that often. Like I just don't think I'm gonna write a loop like this. I'll probably just write the formula myself. I'll probably just write this if this is what I actually want. But like it's just kind of a cool optimization to have, right? So like this begs the question: do I want to add it to my compiler.js, right? But the thing is, the key aspect of implementing this optimization is the SSA part, the static single static assignment, right? Static single assignment, single static assignment. And currently, my compiler follows this pipeline, right? You have the C and header files, the lexer and preprocessor tokenizes it, and then the tokens are parsed into an AST, and then the AST has a couple lowering phases, like getting rid of the go-tos into a format that's easier for the WASM to consume, and then we cogen that into the WASM. And then we convert the tree into a WebAssembly. I'm in the process of adding an IR phase that is essentially like a tree structure. So the AST is a tree structure that mirrors the C code. The IR is meant to be a tree structure that better resembles the WebAssembly code. The IR tends to be a bit simpler and easier to reason about than the AST, and so it makes for a good tool for optimizing. At least doing this sort of optimizing that kind of is like a little bit easier to imagine, like constant folding, basic constant folding, and like inlining certain function calls, so on. So I'm in the process of doing that. But in order to be able to implement this specific optimization, I actually need to have an extra phase here, right? Essentially, I need to have the IR, and then I need a phase that converts the IR into SSA. And then in the SSA, I'm going to do some optimizations on it, possibly SSA, and then I might need a control flow graph as well. I'll have to think about that. And then after doing the optimizations, I need to convert it back into IR, and then from IR, I'll do the code gen. Maybe at some point, if like I need those optimizations, maybe I will really have to do that. But at this point in time, I feel like this is not the direction I want to be going in, and like it is hairier. Like at least conceptually to me, maybe smarter people might disagree with me, but the AST is pretty close to the C source. And then even the IR, even though the intermediate representation is meant to be closer to how WebAssembly, raw WebAssembly views things, I still find the IR to be quite close to the human readable code, right? But once you're taking stuff down into SSA, you get, like, you saw it, right? Like, the code is gonna look like this, right? Whatever this is, right? Like, yeah, you can kind of see the pattern. Okay, like, all the variables kind of explode into multiple variables, and then you have all these phi's everywhere, and then you have to kind of think about, like, what what do phi's mean, right? So you're gonna have, I'm gonna need an internal representation that I feel like is going to drift quite a bit from what the original sources up here are like, right? Yeah, it can be done. It is doable, but it is also something where it adds, in my opinion, quite a bit of complexity that is unnecessary at this moment. So it is a kind of a shame. I would have loved to have a demo where it's like, oh yeah, look at my compiler, like, optimizing away this loop. But alas, this is just me complaining. Yeah, this is just me trying to justify my compiler not having the coolest optimizations. But who knows? Never say never. You know, maybe at some point it'll be added. Yeah.